So let's take a look at how these two velocities are related. So to relate these velocities, we're going to consider a circle. So let me redraw a nice circle here. Right? Again, we have some radius length, right? And the linear velocity is the speed in which the object goes at some point on the edge of the circle. All right. So again, when we sweep out an angle, so let's just say we've swept out that angle theta right there. Right? What we've also done is I did that rotation, as we've seen, we have swept out some arc length. So we call that S. And again, remember, this is our distance that we traveled. So when we sweep out that angle, we have the distance that was traveled, and we have the angle that's rotated, right? And then we also have some time frame that all occurred. Maybe it happened in 1 second or 2 seconds or 3 seconds, right? And so what we end up having, right, is individually we can take the S and divide it by time. I can take the theta and divide it by time, right? So we had the our linear velocity was S divided by t, and our angular velocity was theta divided by t. And so we can easily see that there's got to be a way, right? There's got to be an equation that relates those two velocities, because we can see them in action on the same circle as we go through some rotation per unit time. All right, and I hope you guys have watched the video at this time. Let me draw another circle. So what we had on this merry-go-round, right, is that was connected, and this is another story here, but it was connected to another tire on a motorcycle, and this guy was rotating a lot. And that rotation basically caused this guy to rotate on the merry-go-round. And what you were seeing, right, eventually what ended up happening to the poor individual, right, the forces got too much and the guy flew off, and you'll notice he flew off in a direction of travel. And that's what's kind of a little bit confusing about the linear velocity, because linear velocity, being a line, is along a line, but we are also connected to a circle. So so the way we're talking about linear velocity here, we can physically see it, as you saw the poor kid fly off the merry-go-round, right? He flew off in the direction that the linear velocity was going, right, at that particular time. Although if you have enough strength and you can stay on, that linear velocity, you kind of feel it on the edge of the circle as you sweep out your distance. And of course, what's also going on, right, is your omega. So that's what's happening picture-wise with regard to this. So, what you can experience, all right, well, how about, I'm going to set up the stage to do that, but here's kind of what's going on. Of course, on this tire, we had the same thing, right? On the tire, we had another omega going on. How about we call that omega 2 and this omega 1 and velocity 1, and then there was some linear velocity acting in the same direction, right? As a matter of fact, since the tires are touching, these two guys are equal to set up a problem that we're going to be doing here in this particular section. But we have two different angular speeds. We have two different radiuses, right? A small motorcycle versus a radius of a merry-go-round, but their velocities were actually the same. And that's going to be very important for us later on today. But the idea then is the velocity is experienced along the edge. As you saw the poor guy in the video, if you let go, he's going to go flying in the direction of that linear velocity. But if he has enough strength, he will actually experience that linear velocity along the edge. So distance traveled this way or distance traveled that way gives me my velocity. And of course, how fast I'm spinning gives me my angular velocity. So let's put this all together. So we're actually going to go back to section 3.2, where we learned that the arc length, for our case, the distance traveled, right, is equal to the radius of the circle times the central angle that I swept out, right? So basically this picture right up here. And this is how easy it is to relate these things, because if I take that formula and I just divide both sides by a time value, what we end up getting if we rewrite it is S over T. How about I write this as R and theta over t, right? So I'll rewrite that as that, right? R over 1 gives us the same thing. But S over t, that's our linear velocity, and R is our radius, and theta over t is our omega. So we have our famous formula that relates my linear velocity to my angular velocity. And we see that they're directly proportional to each other. It just basically takes the radius. So back to my picture up here, this is what's happening on a circle, right? If my radius is relatively small, then the linear velocity that I'm going to experience, right, perpendicular to that would be small. But if my radius gets a little bit larger, then my linear velocity is going to get a little bit larger. And if we're at the edge of the circle, right, the linear velocity that I experience is even going to be larger. So here's your linear velocity for different types of radiuses as we get larger and larger and larger outside the circle. And I don't know if you guys have ever been on a merry-go-round, but I'm pretty sure if you guys have ever been right in the middle of the merry-go-round as you spin it, you're definitely going to get dizzy as you spin, right, as you experience some omega, but your linear velocity is very, very low because you're really close to the center. But as you get closer to the edge of the merry-go-round, right, you start to experience more linear velocity because that's what the formula says you should be experiencing, and you start experiencing a lot of forces. You know, as you guys take physics, right, if you take your mass times your velocity, you know, you end up having a lot of interesting things going on. I think you have what's called momentum, all right, and so you start feeling some forces interacting with yourself, and torque and all that other great stuff. And I'll leave that to your physics classes. But this formula basically shows why is that the case. So fix your angular speed, right, and then let your radius get larger, then your velocity is going to get larger. Of course, I could also fix the radius and just start spinning faster and faster and faster, which means my linear velocity at the edge is also going to go faster and faster and faster. And as you saw in the video with the poor motorcycle, at some point, you know, you can't handle the forces and you'll fly off. So hopefully the video helped you see it in action. Hopefully I've tied this all together. To kind of wrap up before we start doing some homework problems and whatnot, right? We basically have three pretty important formulas in here, right? Our linear velocity being the distance that I traveled over time, my angular velocity being the angle that I rotate over unit time, and then the formula to how I relate it. My linear velocity is the radius of my circle multiplied by the angular velocity. And we'll basically be using these like crazy and some other techniques and some homework coming soon. So we're 7 minutes, almost 8 minutes into this, so why don't I pause? I'll do these examples in another video coming soon.